chapter is called Work and Energy. In this first section, we will talk about the work being done by a constant force. So we will basically have some constant force, it could be almost anything, and it would be applied to some object, and the object is going to be moving. So in a physical, in the terms of physics, for work to be done, we have to have two things to occur. We have to have the object has to move, so it has to be moving, and we need a push, some type of a force. It could be the force due to the weight, which would make someone fall. It could be the force done by an applied force, if a person pushed something across the floor. It could be the force done by friction, where the friction is trying to oppose motion. It could be the net force. So there's many different types of work that could be done. In fact, for every individual force that you could name, there's work associated with that particular force, as long as the object is moving through a distance. So in physics, the way we define work would be this way. We would say that work, well, first of all, let me say work is a scalar. It's not a vector. There's no direction associated with work. And we give work the capital letter W. So in a formula, we would say work equals a force, and in the book, they use the letter D. Now, many books use different letters. I've seen this many places where they just call it X. D is good because we're not really talking about vectors, we're talking about scalars. So D would be here for distance. And it's going to be in meters. And this would be some type of a force. And this thing here would be in newtons. And this here is the symbol for a parallel. So that's a math term. And what they're saying is they want the force, which is going to be parallel to the direction of motion, or the distance that it's moving through. So if it's moving through a horizontal distance, we only want to be concerned with the horizontal force. If it's moving through a vertical distance, we only want to be concerned with the vertical force. And this thing here is work, as I've said earlier. And work has units of newtons times meters. So it's a little bit different here. You've never really seen this type of a symbol before, that little dot, and it really does mean something. But at this level of physics, we would just call it newtons times meters. If you were taking a calculus-based physics, this would mean the dot product. They're actually going to take a certain way to work with vectors, and they're going to do something called the dot product to them. So that's why you see a little dot here. But it really does mean multiplication. So we're going to multiply the parallel force, and when I say parallel force, the force that is parallel to the direction of motion or to the distance that it's going to be going. Okay. There's another way to talk about these. By the way, the units came from force, has units of newtons, and distance has units of meters. So that's where we get the newtons dot meters. But we can also say joules. So a more common way to talk about this would be with this capital letter J. Capital letter J is the unit that we would use for all things called work, and very soon we'll see work and energy are similar. So capital letter J comes from a person's last name. There was a man named James Prescott Joule, and we pronounce this here Joule. So when you see the capital letter J, we say there's so many joules of energy stored up in a certain there's so many joules of energy involved. So when there's different types of energy. We can have energy of motion. We could have energy of height. We could have energy of sound. We can have electrical stored up energy. So we're just going to be talking about a couple of types of energy in this chapter. But before we get to energy, we have to figure out something about the work. So when I say parallel again, it would be something like this. If somebody were to push on a box in this way, you can see that if the box is going to move, it's going to slide along the ground, and it'll be sliding this way. So this would be the direction of motion. So if we want to know what is the angle, well, usually you'd be told what this angle is right here. So this would be the way they would talk about the angle. So the way we would write this is we don't want the whole applied force. We only want the component down here. Let me move this. So you see, if you look at this, you could say which two ways is that force pushing as far as this is the ground here. So the two ways that this thing is pushing, it's pushing to the right and it's pushing down into the ground. So that's a vector. Every force is a vector, and I could rewrite it as two different components. I could write the component going down and component going to the right. So the component going to the right would be called the force in the x direction. Okay, so how would I get this? I would do from chapter 3, when we learned about trigonometry and how to break a vector down into the x and y components. I could say, here's my angle, and this is my adjacent side. So there was a formula back then that said the adjacent side is equal to the hypotenuse of the triangle times the cosine. So this would actually equal the force applied times the cosine of the angle. Okay, so if that's the case, then we could rewrite this. And here's the parallel. And so we could rewrite it and say that the work is equal to the force times the distance times the cosine of the angle. Okay. And this angle right here is defined as the angle between the direction of motion and the direction of the force. So theta is the angle between the direction of motion and the direction of the force. And no matter which type of force we're talking about, we will have a corresponding amount of work. So if they talk about what is the force of friction, if they talk about how much work is being done by friction as you slide a box across a certain distance, well, if you know what the frictional force is, and you know what the distance and the angle is, you could find out the work done by friction. So whatever force we're talking about, so if we have a little subscript, let me just put this little box here. Whatever subscript would go into that box, if it's the force called the weight, the force normal, the force applied, the force of tension, the force of friction, whatever force, the net force. So if you talk about the net force, whatever force would be here in this box, this would be the same thing. So I'm just showing you that for every single type of force we could have, we would have a certain amount of work done by that particular type of force. So you just have to keep these subscripts together. I have a word problem here behind me which shows a picture of a box, and it says the mass of the box is 50 kilograms, and it shows a force that's pushing with an applied force of 115 newtons, and it doesn't show it here, but I meant to put that they were pushing this box at a 30-degree angle below the horizon. So somebody's in front of this box and they're pushing. Somebody's in front of this box and they're pushing downward. So the box is being pushed down and to the right. And over here, it gives us the coefficient of kinetic friction. They say it's 0.174, so it's somewhat of a slippery surface, I guess. And they're saying, find the work done by all the forces, by each. It should say by each individual force. So how many forces are there? Well, we have to use this thing called a free body diagram, which we learned about in chapter 4. So chapter 4 said draw each of the forces acting on the body. So what other forces are there? Well, there's always weight. Weight here is pushing this thing down. So weight is pushing this down, so the weight is mass times gravity. So with your calculators, if you took 50 kilograms times 9.8, you'd come up with 490 newtons. one of the first things I should have done was break this up into the component pieces. So this force right here is pushing down on it, and it's pushing to the right. So since Chapter 3, we've been able to break things down into the x and y components, the base and the height of a triangle. So if the hypotenuse is 115 and the angle is 30, the base would be the hypotenuse times 30. So if I want to get the base, I would say it's the hypotenuse. So the force applied in the x direction would be the hypotenuse times the cosine of the angle, which is equal to, plug it in, we have 115 newtons times the cosine of 30 degrees, and I'll plug it in my calculator. It comes out to be 99.6. If I wanted to figure out what the y piece was, I would look at this piece right here and I would say the force applied in the y direction would be the hypotenuse times the sine of the angle, which is 115 newtons times the sine of 30 degrees, and that comes out 57.5. If I wanted to know what the normal force is on this object here, I'd note that the weight is pushing it down into the ground. But so isn't this piece, so isn't the vertical piece. So this is pushing it down into the ground, and this is also trying to push it down into the ground. So if I add those two together, I'll figure out how much the ground is pushing up on it. So the ground pushing up is called the force normal, and the normal force is basically 57.5 plus this one right here, I'm sorry, the weight, 490. So the force normal is going to be 490 newtons plus 57.5 newtons. And that comes out to be 547.5. And if I wanted to know what the force of friction is, well, the force of friction is the force that occurs between the two surfaces where the sliding occurring. So between the two sliding surfaces, I have a force of friction, and it'll be going this way. So where the box is in contact with the floor, I would have a force of friction going this way. So the force of friction has a formula, which is defined as mu times the force normal which in this case, you just plug it in. Mu is given up here, so it's going to equal 0.174 times the normal force, which was right above it, 547.5 newtons, and when I plug those things in, I will get 95.3. So there's my force of friction right there, and I can put that into the picture. So the force of friction equals 95.3. So now I have all the forces that could possibly exist in this picture, and now I could go and calculate how much work is being done by each of these individual forces. I've gone and I've changed the problem wording just a tiny bit. So what I've done is I've erased what was behind me. I've listed all the forces in the picture. So we have the force of weight, which was 490 newtons. We have the force normal, 547.5. We have the force of friction, 95.3. We have the force applied in the x direction of 99.6, and so forth. So I'm asking now to find the force done by each force. So find the work being done by each individual force. So this is what I meant when I said the subscript. So the work being done, I should say if I move the box across the floor, say 75 meters. because the definition of work is one of the things. You definitely need the object to be moving. So I can't just say there's all these forces. I have to figure out how far it's moving. So to figure out the work on this one, I'll say the work done by the applied force is going to equal the force applied. It's going to equal times the distance. And it's going to equal the cosine of the angle. Okay. So in this particular case, the applied force is really 115 newtons. The distance it's moving is really 75 meters across the floor. And the angle, when we said the angle between the direction of motion and the direction of that particular force. So that particular force is pointing this way, and the direction of motion is going to be this way. If I drew a Cartesian coordinate quickly, I would see this. The direction of motion would be going along this way, and the angle would be, in this case, 30 degrees below the horizontal. So I would draw the angle this way. So as you can see in this picture, the motion and the force are separated by an angle, and I just wrote here theta, but that theta would be this angle right here, 30 degrees. So I'd put in here the cosine of 30 degrees. Okay. Let me erase this picture here. When I do that on my calculator, it comes out to be 7,469.5. So this is a positive number, 7,469.5. And it's Newton meters, or you could call it joules if you wanted to. So that's the work being done by one of those forces, the force of the applied force. How about the work done by friction? So if I said what's the work done by friction, I could write it out. The work done by friction, and friction is a force. So I'm just going to plug in the numbers. So the applied force, so this is going to be the force of friction. So in this case, the force of friction is 95.3. And the distance that the box is going to slide through is still going to be 75 meters. And the angle, well, I have to plug in an angle. So again, you could draw the Cartesian coordinate system. In this particular case, the box is going to move to the right. So if I go right to the center of the Cartesian, motion is this way. And the force of friction is pointing to the left. So going this way would be the force of friction. So what would we call? So what would we call the angle between a vector going to the right and a vector going to the left? We would call that 180 degrees. So I would go right up here and say the cosine of 180 degrees. And I would plug that into my calculator. When you do the math for these three, it comes out to be negative 7,147.5. Okay. What other forces do we have? Well, we have this force called weight. So we could figure that out. So the work being done by the weight is, well, the weight of this thing is 490 newtons. The distance the box is physically going to move through is 75 meters. The cosine. Now we need to figure out what angle we're talking about. So for the last two cases, I've drawn this thing called the Cartesian coordinate system. So again, if I draw the Cartesian coordinate system, the box is going to move to the right. So that's going to be motion. And this weight vector, this force vector, is pointing straight down. So this is the force of weight. Well, what is the angle between those two arrows? If you just look at it, the angle here would be considered 90 degrees. Some might want to call it negative 90, but it's just the physical angle there. They're differing by 90 degrees. And I would say the cosine of 90 degrees here. So when you take out your calculator and do that, you'll find that the cosine of 90 degrees comes out to be 0. So let me take away this Cartesian coordinate system thing. This thing comes out to be 0 newtons meters. By the way, the unit here was meters. This was a Newton meter. So this is 0 Newton meters. And if I did the other one too, the work being done by the force normal, I would plug in different numbers, but, you know, overall, the cosine is going to be of 90 degrees again. The normal force here is pushing vertically upward, and the box is moving towards the right. So the angle between going to the right and going upward would be 90 degrees, and that means this is going to be 0 also. Okay, so there we have all those different ones. If you were asked, a standard question might be to ask, say, what is the total work being done on this box behind me? If that was the only question, you could go and you could find out what is the total, what's the net force. If you know the net force, you could plug in the force net times the distance times the angle of 0, and you'd come up with something. In this case, we could say the work net equals, it's basically if I drew a line here. And you see, work, I sometimes like to equate work and energy, those ideas, with money. You see, you know, people have jobs. Many people have multiple jobs, so they have money coming in different ways. And many people, everyone that I know has bills. So bills are when you have to spend out some of your money. So most people have money coming in, possibly a few different jobs, so they have money coming in a few different ways. Most people have multiple bills, so they have money going out in many different ways. And in this particular case, I would say if you consider it a positive number, you're doing work. You're doing positive work on the system. So this is the amount of work that you are doing. You're giving it to the system. So the system is gaining this thing called work or energy, but you're losing some. So if you were to push a box across a floor for a long distance, for a long time, you would be getting tired. You would be feeling weak. You would be feeling depleted of energy. And that's what's happening here. There's energy going into the box because you are using up some of your own energy. So you're giving up some of your energy, and it's going into the box, which helps push the box along. And to me, it's kind of like taking money and putting money into your savings account. So you put in a huge amount of money into your savings account. But here, you see there's energy, there's work being taken out. Friction is trying to oppose motion, and friction does not make things easier. Friction makes things harder to move along. So friction is going to take out an awful lot of this work and energy. It's just like if you put a large sum of money into the bank, and then the next few days you have these huge bills, you might have to spend a lot of the, you might have to take the money out of the bank. So I considered positive work to being energy going into the system. Negative work is when something is taking energy out. And the network, when we talk about the network, you could talk about a person's net worth. How much money do they have altogether when you consider all the things they own and all the things that all the money that they owe to others. So if we just add these up, take this number and add that negative value to it, you'll come up with some amount, and it comes out to be a positive 322 Newton meters. That's my net work. Okay, you may think that that's terrible, and I would agree with you. That doesn't seem too good at all. Okay, so what I just did on my calculator, I just tried to see how bad this was. If I took the number 322 and I divided it by 7,469.5, I come up with about 4.3%. That would be terrible. If I invested in something, if I decided to put $7,469 into something, and before I know it, my stock or whatever is worth $322, then that would mean I would have lost most of my money. I would only have kept 4% of all the money I put in. That means I lost like 96%. In real life, many things that we use, they talk about the efficiency of those devices. So they say a car is approximately 12% efficient. What that means is every dollar that you put into your car's gas tank, 12 cents of it is making you drive forward. What happens to the other 88 cents? Well, it's useless. It's being used up by heat in the engine, and where basically the friction in the engine is eating up most of that useful energy. So they say a car engine is 12% efficient. That means it's 88% not efficient. In this particular case, we pushed a box and we put in an awful lot of our energy, and what happened was the friction in the ground, between the ground and the box, took out a lot of that energy, and we were only left with this tiny amount. Okay. But if you look up here, just before I leave this problem, if you look up here, going to the right was the number 99.6, and going to the left was the number 95.3. So if we subtract those, we would have gotten 4.3. So just by looking at that up there, I can see that the net force would have been 4.3. So if I just erase that to show you how they compare, let me just take all these away for a moment, and just say, I'm going to take all of them away, all the forces, and just say that the net force equals 4.3 newtons. And then I want to see how much was done by the net force. I could do this. So you can see if I say what is the work net, then I would have to take the force net, multiply it by the distance, multiply it by the cosine of the angle. So this would be 4.3 newtons. The box will physically move through 75 meters. And the angle in this case is 0. The reason why it's 0 is someone is pushing this box to the right, and the box is moving to the right. So if you had two arrows both going to the right, then there would be no angle between them. They would be overlapping each other. So the angle would be 0. If I multiply this on my calculator, 4.3 times 75, it comes out to be 322.5 newtons. It's almost the exact same as this. So it's someplace I must have rounded a decimal point a little bit up or down. So it's not exactly the same, but if I had kept every decimal point, these would be the exact same.